So in our previous videos, we took a look at the difference between synchronous and combinational circuits. Um, in the next set of videos, we're going to start putting our synchronous circuits to work. So we talked about how latches and flip-flops work, but we haven't actually used them to accomplish anything for us just yet. When we want to use latches and flip-flops in our circuits, one way to model that behavior is to use what's called a finite state machine. So the next several videos are going to cover finite state machines, how to create them, how they work, and how to design circuits that use finite state machines as a high-level basis. So let's first talk about what a finite state machine contains. There are four main parts to finite state machines. We have the states themselves, which dictate where we currently are in our circuit operation. So what is the current state of the system that we are trying to model? We have our inputs, right? And our inputs are going to dictate how the machine behaves in conjunction with the state, right? And then we have our outputs, which is what we are telling the outside world. What are we telling them based on our current state? And then finally we have transitions, which are a function of the state that we are currently in as well as the inputs. So depending on where we are and what information we are receiving, we're going to dictate where we go next, which state we are going to be in next time around. So if we condense this down to a high level, here's what a circuit might look like that's modeling a finite state machine. We see that I have all four pieces on this particular diagram. Our inputs are over here, as you can see, right? Our outputs are on the right-hand side. Now, for the next few videos at least, we're going to focus primarily on synchronous outputs. Eventually, we'll work asynchronous outputs into the mix, but for right now, we're just going to focus solely on synchronous outputs, right? The state itself, where are we? What is our current position? That's represented by the flip-flops. So the flip-flops or the registers are what dictate where we currently are in terms of state. And so then the transitions are represented here, right? You see that the current state, in conjunction with the input values, dictate the next state that we will be in, right? So this is a very high-level view of how a finite state machine circuit works. Let's take a look at some finite state machines, and then eventually we'll talk about how we can actually convert finite state machines into fully functional circuits. So here is a finite state machine. Here's an example of a finite state machine. And I want to explain to you how this finite state machine works, but before I do that, let me take a minute or two and describe the different parts. So the circles, the ovals themselves, are the states. This is where we currently are within the system, right? This is where we currently will be within the system. You see, this one is lightly colored. That means that's where we're going to start. That's going to be our initial state. Sometimes you might see an arrow pointing to the starting state instead, right? So if you see an arrow pointing to the starting state or a lightly colored state, that is our initial state. That is where we begin, right? The arrows dictate transitions. So remember that transitioning from one state to the next depends on where I currently am, as well as what my input values are. So along with every single transition, I see a set of inputs. In this case, I have 2 bits of input information, and that dictates where I go next. You should also notice about these transitions that they are directional, which means they can only be traversed in one direction. I can only go in the direction that the arrow is pointing. I cannot go backwards across a transition. It's very important, right? And then finally, the last piece of this finite state machine is the output. So inside of each state, you see it has a name. This is the name of the state. And then after the slash is the output. So I have 2 bits of output, right? So what is this finite state machine trying to tell us? Well, this finite state machine is what is called a fair arbiter. Imagine a case where we have one resource, maybe a disk, right? And then I have 2 processes that want to use that resource, that maybe want to write some data to that disk, for example. But in our hypothetical situation, the disk can only accommodate one write operation at a time. So if we allow something to write to the disk, the other process is now locked out. The other process cannot write to disk at that current moment in time. So what this finite state machine is trying to model is who should be able to write to that disk at any given point in time. And if we have a tie, right, if we have a request for the disk at the same time, we're going to give precedence to whoever has gone without writing to disk the longest, right? So let's walk through a couple of situations in this finite state machine and what they mean. We're going to start in this idle zero state, right? This is our first state where we begin. And so you see I've got a few transitions, 3 as a matter of fact, coming out of this state. Let's take a look at what each of those mean. You see these arrows here, right, pointing to the inputs, and I've got another set of arrows pointing to the outputs. So what these input bits mean, the leftmost input bit means that process number 0 has requested use of the disk. The rightmost bit means process number 1 has requested use of the disk. And then for the outputs, right, the leftmost output bit means process 0 has been granted use of the disk, and then the rightmost bit means process 1 has been granted use of the disk, so G0 and G1. So if we take a look at our initial state, we see that neither disk has been granted access, or neither process has been granted access to the disk because nobody's asked for it. And this first transition, looping back to itself, says that if neither disk requests access, if neither process requests access to the disk, then we are just going to remain in this idle state until the process actually requests access to our disk. And so the other two transitions reflect those requests for access. We see I've got one over here that says if process 0 requests the disk, then I will give them access. I go to the busy 0 state and I see that the grant 0 bit is set, right? Otherwise, if process 1 requests access to the disk, then we see that we go to busy 1 state and we see that process 1 has access and process 0 does not. Now, one of the inputs here in this particular transition, right at the top, is an X. And that means that we do not care what the value of that bit is. We do not care what the value of this particular bit is. So that means that if process 0 requests access to the disk, then it does not matter if process 1 is also trying to request access to the disk. We are going to give the result to process 0. So that's how we're breaking ties, right? If we see that both request access at the same time, I'm going to give access to the process that has most recently accessed the disk, that has most recently used this resource that we are trying to control, right? So let's assume that we take this transition. I'm going to take this transition over to the busy 0 state. Let's take a look at what can happen from there. As long as process 1 needs this resource, needs access to disk, then we are going to give it to them. That's what this transition here means, this self-loop, this self-transition. So as long as process 0 wants access, they can get it. As soon as process 0 says, I don't need access anymore, right? I am done with access, then we move over to the idle 1 state. We move over to this particular state here, right? And we see similar transitions then from the idle 1 state that we saw for idle 0. We see that if process 0 requests the disk, then it will access it. If process 1 requests the disk, then we will allow them to access it instead. And busy 1 then also reflects similar transitions to busy 0. So why do we have these 4 states here? Why do we have 4 states when it seems like maybe 2 could get the job done, right? Well, we need 4 states in this particular case to enforce our rule that if both processes request access at the same time, then we need to give precedence, right, to the process that has not accessed the disk most recently, right? Who has not used the disk for the longest period of time. So idle 0 actually represents the state where process 1 was the previous process to access the disk, and idle 1 represents the state that says process 0 was the previous process to access the disk, and you can see that the transitions then favor the other process through the use of these don't care bits. Take a few minutes and study this finite state machine. Make sure that you understand how it works, right, before moving on in this video. So once you are satisfied with the operation of this finite state machine, I'd like to show you a few other things that you can do with finite state machines. The next thing to take a look at with a finite state machine is a transition diagram. On the left side here, you see we have our fair arbiter finite state machine. On the right, we see a transition diagram for this machine. Now, these diagrams look an awful lot like truth tables, but they're not quite the same thing. Over here, we see I have the states listed out, just their names, right? Then on this next column, I see the input values for both of the request bits that I have. And then on the right-hand side, I see what the output value should be, as well as the next state that I should be transitioning to. This table here displays the exact same information as the finite state machine here. The only difference is how it's displayed. These tables, these diagrams, can make things a little bit easier when converting your finite state machines into circuits, which is something that we're going to talk about a little bit later on. Finally, the last thing that I'd like to show you is a timing diagram for this particular example. Again, you can see I have the state information, the state diagram over here on the right-hand side. And so the question is, what state are we in as we progress through these different timing sequences? Now, the first thing that you should know is that for every single finite state machine, right, our state can only change on the rising edge of the clock. Our state can only change when the clock goes from low to high, right? And that is because our state is being stored in a register or a series of flip-flops. And flip-flops can only change their output when the clock signal goes from low to high. So with that in mind, let's take a look at what our inputs are and see if we can figure out what states we're in at each rising edge of this clock. So for the first rising edge that I see here, I see that my inputs are both 0. Nobody's requesting access to disk. I start in this state. This is my initial starting state, right? And because nobody's requested access to disk, I'm going to follow this self-transition, this transition to the current state, and I'm going to remain in the state that I'm in, namely idle 0. The next time I see a rising clock is right here, and I see that process 0 has requested the disk. So what that means is that I'm going to follow this transition over to the busy 0 state. You can see that the inputs here match, right? Process 0 has requested it, so I'm going to give it access to the disk. And the output accordingly should be 1 for the grant 0 bit and 0 for the grant 1 bit. And from our timing diagram, we can see that that is in fact the case. On the next rising edge of the clock, I see that the request bit has gone low again for process 0, and the request bit for process 1 is also low. So I will transition from the busy 0 state over to the idle 1 state. On the next rising edge, I see that both request bits have gone high. So if I look at the transitions that I have available, I see that I've got one back to busy 0 if process 0 requests, but I have another one over here to busy 1 if process 1 requests access. And because we are in the idle 1 state, right, this transition is going to win because we are giving precedence to process 0, process 1 rather, since process 0 already had access to the disk previously. So we're going to give access to this disk to process number 1, and we can see based on our outputs that that is in fact the case. So as long as process 1 wants access, it will get it. We can see at the next rising edge, right? Both requests are still high, but since process 1 is currently using the disk, we are just going to allow process 1 to continue using that disk. Then in the next rising edge, the next clock cycle, we see that request 0 is high, so process 0 still wants access to disk. The request signal for process 1 finally goes low, right? But we cannot give access to process 0 right away. There is no transition from busy 1 to busy 0. We are forced actually to go to the idle 0 state first. And so what happens is the grant output bit for process 1 goes low, but process 0 doesn't get access to the disk either. We are currently in the idle state, which means nobody has access to our resource. Nobody is accessing our disk. If we want to give access to process 0, then we would need at least one more clock cycle, which is not shown here, right, before process 0 would be able to access that disk. So hopefully this video has given you some good information about what finite state machines are and how they operate. In the next video, I'm going to show you how to design your own finite state machines, and then in the video after that, I will show you how to create circuits based off of finite state machines.